I'm Annabelle Nyberg, and this is my submission for Physics 2212 Lab 4 Magnetic Braking. So the purpose of this lab was to analyze the interaction between a tube of aluminum foil and a falling magnet. The materials I used were a bar magnet, aluminum foil, meter stick, and then Python to create a simulation. My findings were that the calculated time that the bar magnet spent within the tube was 0.474 seconds, and then the simulation time was 1.251 seconds. The main physics principles that we're using are Faraday's law, which tells us that a changing magnetic field will induce an electromotive force, and the Biot-Savart law, which tells us that magnetic fields are connected to electric currents traveling through a length of mass. We'll also be using Newton's second law since we're analyzing a falling object. Our assumptions in this lab were that we were to neglect air resistance and that our bar magnet would be acting as a dipole. So the experiment conducted in this lab was I dropped a bar magnet inside a tube of aluminum foil and timed how long it took for the bar magnet to travel all the way to the bottom of the tube. And then I did that 5 times, notating the time it took each time and then calculating the average, which is shown there. The mass of my magnet was 40 grams or 0.04 kilograms, and then the dipole moment was 1.278, which was calculated in lab 2. The foil length was 0.3 meters, the inner radius was 0.015 meters, and then the outer radius was 0.02 meters. All right, and then for our simulation, you can see there, like I mentioned before, that our times calculated were very different, with the simulation calculating at 1.2 seconds. You can also see on the velocity versus time graph where velocity is constant. That is where the magnetic force and the gravitational force have equalized. So velocity has become constant, whereas the areas on the graph where there is slope, that is where the force of gravity is greater than the magnetic force. So the velocity is changing. You can also see on the left there my different pieces of code used to calculate forces and fluxes within the system being the bar magnet, and then the surroundings being everything else. All right, and then to interpret the simulation, so the picture shown before was at the end of the simulation when the bar magnet had reached the bottom of the tube, and you saw that it had a blue ring. When the bar magnet entered the tube in the simulation, the ring was red around the tube. Those colors relate to the different directions of our current. So the red is related to a counterclockwise current, and the blue is related to a clockwise current. So if we were to flip our system around, the direction of those currents would be reversed. So red would be clockwise and blue would be counterclockwise. And then how does our simulation time relate to the computational time? Again, like I said, the simulation time of the time that the magnet spent in the tube was much greater than the actual computated time in the experiment. That could be for a variety of reasons. So sources of error could be my ability to accurately drop the magnet and measure the time it takes to reach the bottom at the same time. So there could be error there. Also, like I said, our dipole was calculated in lab 2 earlier in the semester. So if that calculation was wrong, that could have led to errors in our simulation calculations, as that figure was used in the code. And then also there could be errors because air resistance wasn't accounted for. So final questions. What is the resistivity of the conductor were reduced to as close to 0 as possible? That would increase the magnetic braking in the tube and also increase the time the magnet spins in the tube. And then what if holes were cut into the tube? That would decrease the magnetic braking and decrease the time the magnet spins in the tube. Thank you.